Good morning all. We'll continue our discussion on the shear strength of soil. In the previous video, we started our discussion on what shear strength means. We discussed compressive, tensile and shear stresses. We extended our discussion to the Mohr-Coulomb envelope, the Mohr-circle method of determining sigma and tau, and also we mentioned what the shear strength parameters of soil are, the C and phi. In this particular video, we'll try to briefly discuss the various laboratory tests available now to arrive at the C and phi parameters. The first test is the direct shear test. In the direct shear test, you have a direct shear box which is usually 6 cm by 6 cm in plan and usually about 4 cm in depth. So it's called a direct shear test because you are applying shear stress directly into the soil mass. In the earlier videos we said that rarely soil is applied directly by the shear stress, and usually what happens is the compressive load, when acted upon an inclined plane, is transferred as a shear stress. But in this particular test, we are directly applying a shear stress onto the soil. So this box is having two portions, a bottom box and a top box, and you can have a relative movement. In a sense, the bottom box will move when the machine is operated and the top box stays there. So the bottom box is moving on a set of rollers and the top box stays there, and you're applying a stress onto the top box. The actual photograph of the laboratory direct shear test apparatus is shown here. So you have a shear box which is split horizontally, and the soil sample is filled between a set of porous stones or porous plates. The lower half of the box, this portion, moves and the deformation is measured by a dial gauge setup, and the shear stress is measured by a proving ring. So you have a proving ring here which gives you a certain reading that will indicate the shear stress acting on this plane, and you'll have a dial gauge assembly which will give you the deformation. So in this photograph you can see the proving ring here, and there'll be a dial gauge setup somewhere here that will give you the deformation. So here this photograph shows you how the sample is being prepared. You have a split box, you fill it with sand or soil, and then you have a top cap which is called as a pressure plate, and above which you keep a ball. Though the detailed discussion of the direct shear test is beyond the scope of this theory, and you'll definitely have to deal with the laboratory test when you enter the geotechnical laboratory, I'll try to briefly discuss what this setup is all about. You have a motor assembly here and you have a lever arm assembly here, which gives you an option to place the loads onto a loading pad. Now this load, when you place on the loading pad, gets multiplied with the effect of this lever arm, and the weight is transferred onto this point. So this point will have a connection to this ball, and in short the load P shown here is due to the load that comes above this load mechanism, the loading pad, the lever arm, and then to this frame. So when you place a weight onto this loading pad, it gets transferred through this lever arm, gets multiplied, and it gets transferred to this frame. So this frame comes over here. In the schematic picture, P is the stress or the load that gets applied onto the pressure plate. So this pressure plate uniformly distributes that load, and it becomes the normal stress on the soil, and let that normal stress be sigma 1. So at this point you have sigma 1, the stress that is getting applied onto the soil, and then you apply a shear stress on the box. So that shear stress is getting applied due to the mechanism of operation of this machine. So when you operate the machine, the bottom box starts to move, which means it shears the soil at this plane. It shears the soil with a shear stress that you can read from this proving ring. So you have this normal stress sigma 1, and once the test is completed, you'll have a shear stress tau 1. That is reading number 1, sigma 1 and tau 1. Once that test is completed, when the soil is completely sheared off, you take the assembly back, rearrange the soil and the loading pad mechanism, and then you keep the entire assembly again for the second set of reading. And for the second set of reading, what you do is you increase the load that you apply on the loading pad. Earlier, let's say it was 5 kg, now you apply 10 kg. So you have an increased load here, and then you have an increased stress here. Let that be sigma 2. So under sigma 2, you'll have an increased tau value here. So you have sigma 2 and tau 2. Likewise, you continue the test to get at least 3 or 4 sets of readings. Sigma 1 tau 1, sigma 2 tau 2, sigma 3 tau 3, and sigma 4 tau 4, etc. That will help you to give the C and phi parameters, which is discussed here. You have the normal stress sigma and the shear stress tau. So a normal stress sigma 1 is applied and the corresponding shear stress tau 1 is measured. Like this, you have sigma 1 and then you have the tau 1. You will get 1 point here. The next higher load or the next normal stress is applied and tau 2 is measured. Like this, you have sigma 2 and tau 2, the second point. And this is repeated for a few more increments, and you get the best fit line that represents a Mohr Coulomb failure envelope. So you have sigma 1 tau 1 here, you have sigma 2 tau 2 here, and likewise let's say you have sigma 3 tau 3 here. You can draw a line that best represents these 3 points. It need not go through all the 3 or 4 points. It just means that you'll have to have the best fit line like this, right? So that line is a Mohr Coulomb failure envelope, which will have an intercept, which is the cohesion or the cohesive strength, and it will have a slope phi, which is the angle of internal friction. So in short, when you have at least 3 points, sigma 1 tau 1, sigma 2 tau 2, and sigma 3 tau 3, you can draw a line which will have an intercept C and a slope phi. So C and phi are the shear strength parameters that we were interested to find. Now, direct shear test, of course, has got its own merits and demerits. The merit is that the sample preparation is quite easy. This test is quite simple and it takes less duration compared to the others. The apparatus is also cheap. But the few demerits probably outweighs the merits to a certain extent, and hence this is not usually practiced when you are actually interested to get serious remarks from the laboratory test. The demerit is that there's a non-uniform stress distribution on the failure plane. So this is the failure plane which is predetermined, and the stress on this failure plane is not uniformly distributed. The second demerit, which perhaps is a worse demerit, is that the failure plane is fixed. The soil doesn't fail on its weakest plane. Instead, it fails through a predetermined plane. Another demerit is that the pore pressure cannot be measured. Soil is not usually dry all the time. It has water content in it, and it will of course have pore pressure generated when you apply stress. This pore pressure cannot be measured using the direct shear test. The lateral deformation is not allowed. As you can see, it's a box here, and when you apply stress, the box setup doesn't allow the soil to deform laterally, and of course that's a demerit as well.